Hi, and welcome to the 5th tutorial video for this term. This tutorial introduces springs and how to approach them using energy methods. The first problem states, as indicated by the derivation, the principle of work and energy is valid for observers in any inertial reference frame. Show that this is so by considering the block of mass m which rests on the smooth surface and is subjected to a horizontal force F. If observer A is in a fixed frame x, determine the final speed of the block if it has an initial speed of v0 and travels a distance d, both directed to the right and measured from the fixed frame. Compare the result with that obtained by an observer B attached to the x prime axis and moving at a constant velocity of vb relative to A. As a hint, the distance the block travels will first have to be computed for observer B before applying the principle of work and energy. First, let's look at how the block moves in frame A, which is a stationary reference frame. I put some trees in the background of this animation to indicate whether the current reference frame is moving or not. After some time, the block moves a distance d. Let's start with our usual energy equation. The work done on the block is simply force times distance. There's no change in gravitational potential since the block doesn't change height, and the change in kinetic energy is represented by this expression. This gives us a final velocity in frame A of 6.08 meters per second. One thing that will stay constant between the two reference frames is the amount of time that passes. We can find that time using our usual equation for distance traveled with a constant acceleration. The acceleration is simply f over m, since there aren't any other forces in the horizontal direction. Solving this gives us a time of 1.80 seconds. Now let's rewind and see that motion again, but from the perspective of frame B. I'll call the distance traveled in frame B's perspective d prime, and we can see visually that d prime is less than d. Like the question hints, we'd like to solve for d prime. We can use this by using t, or the time change, which like I said is the same whether you're observing from frame A or from frame B. Let's reuse the equation for distance traveled with a constant acceleration. This time, the initial velocity is v0 minus vb, which accounts for the movement of frame B. The acceleration is still the same. Solving this equation tells us that d prime is 6.39 meters. We can then use the energy equation again, remembering to use d prime instead of d, and the adjusted initial velocity. Solving that equation gives us a final velocity in frame B's perspective of 4.08 meters per second. This is exactly 2 meters per second slower than what we found in frame A, which makes sense because that's the speed at which frame B is moving. Now for problem 2. It states, the bob of mass m of a pendulum is fired from rest at position A. If the spring is compressed to a distance delta and released, determine A, its stiffness k so that the speed of the bob is 0 when it reaches point B, where the radius of curvature is still r, and B, the stiffness k so that when the bob reaches point C, the tension in the cord is 0. Here's my recreation. Let's establish the reference height at position A. The first part of the question is asking for the spring constant which causes the velocity at B to be 0. We can solve this using energy methods, but we need to modify our energy equation to include spring energy. Springs store potential energy by being compressed or stretched away from their neutral position. The energy stored is 1/2 k times delta squared, where delta is the deflection of the spring. Let's fill in the terms of our energy equation. No work is done, so the left side is 0. The gravitational potential energy increases by mgr, and the spring potential energy decreases by 1/2 k delta squared. Solving this equation for k gives us 3.53 kilonewtons per meter, which answers the first part of the problem. The next part is asking for the spring constant which causes the string tension at C to be 0. If we fill in the energy terms again, not only is the height 3 times higher, but we need to include the final kinetic energy. We actually don't know what the final velocity is yet, but we can find it using centripetal acceleration since the bob is moving on a circular path. Drawing a free body diagram, we note that the only forces that could act on the bob are tension and gravity. We're told that tension is 0, so let's get that out of the way. And we're left with just gravity. The net force is equal to mass times acceleration, where the acceleration is centripetal, so we can find that the velocity at C is the square root of 2gr. Plugging this into the energy equation gives us a spring constant of 14.13 kilonewtons per meter. Lastly, we have problem 3. It states, a block having a mass m is attached to 4 springs. If each spring has a stiffness k and an unstretched length delta, determine the maximum downward vertical displacement S max of the block if it is released from rest at s equals 0. This problem is really quite straightforward. The block is bouncing while suspended by 4 strings, but as long as we carefully consider each spring, then we won't have any issues. We use the same old energy equation and recognize that both the initial and final velocity are 0 since we're considering the very bottom of the bounce. So, there's no work, a loss in gravitational potential energy, and no change in kinetic energy. Now we have to consider the springs. The interesting part of this problem is that the springs have been pre-compressed, so we have to consider that when we're finding the spring energies. The final stored energy in the upper springs is given by this expression. The final length of the upper springs is L plus S max, and we subtract delta to find the displacement of the spring from its neutral position. There's a 2 in front because of the 2 upper springs. This expression gives us the stored spring energy in the lower springs. This time, the spring length is L minus S max. Lastly, the initial stored spring energy is identical in each spring, and the displacement from the neutral position is simply L minus delta. Solving this big equation for S max gives us an answer of 49.0 millimeters. That's it for today's video. As always, you can contact me at this email address if you have any comments or questions. Thanks for watching, and I'll see you in the next video.